Another regularization techniques for neural networks is batch normalization. Let me give you the intuition on this. So we've talked about normalizing inputs, right? So going ahead and adjusting the inputs so that we have the same range of values. So often what we'll do is set it up so that the mean is 0 and the standard deviation is 1. So we've talked about normalizing input. Maybe we want to normalize the input to other layers as well, besides to the first layer. Let's look at the output of layer K. And let's say this is size 3. How big is the output of layer K? Well, what does it look like? Well, it looks like a vector of width 3. What is the number of rows? Well, that's going to depend on the batch input. So if our batch has 5 training examples, then our input is of the form 5 times something. That is, there's 5 rows. That's going to be fed into each layer, and the output of each layer then is going to be a 5 by something. In the case then of layer K, we're going to have a 5 by 3 tensor coming out. Or tensor, again, is just a multi-dimensional array. If we are working in a convolutional neural network where we're actually dealing with 2-dimensional values coming in or 3-dimensional values, let's say we're dealing with something that looks like, we might have a 220 by 220 by 10 here. Well, we can always add in another dimension to represent the different instances in the particular batch. So we've got this 5 by 3. Okay, and let's look at one particular node here. Okay, so there's the first node, which is going to represent the first column here. And let's just look at some particular values that might come in. So let's say batch number 1. Okay, so it's going to come up, its values might be, let's say, 5, 9, 3, 1, and 15. Batch 2, a different set of 5 training instances, might have, at layer K, the output of the first node might be quite different. We might have, let's say, 100, 32, 0, 3, and 8. So what we can see is that the mean and standard deviation of those are fairly different. Right, let's just kind of look at, let's calculate the mean and standard deviation of each. So 14, 17, 18, 33, 33 of 5 is, so the mean is about 6. And we'll say sigma squared is about, and I'm just making up this number, but it's probably within an order of magnitude. Let's just make it 2. Okay, here for this batch, the mean is much different, right? 132, 135, 143 divided by 5, so that's around 29. And sigma squared is much higher. Let's say it's more like around 10. I am fairly close on the mean, and I am just sort of making up numbers on the standard deviation. But what I want you to notice is let's look at layer K plus 1. So K plus 1 has these values coming in. In one batch, we are going to be getting a set of values with a mean and standard deviation of 6 and 2. In the next batch when you run, we're going to get a much larger mean, and it so happens a larger standard deviation too. But those means and standard deviations are varying quite a bit as we come in batch by batch by batch. So the thought is, let's do some sort of normalization of mean and standard deviation on a batch by batch basis. So that's where we get this batch normalization. And this is also normally just called batch norm. So we know how we would go ahead and normalize this, right? We would take, for batch 1, we would take 5, 9, 3, 1, and 15, and then we would subtract the mean and divide by the standard deviation. And I'm going to just go ahead and call this sub 1 and sub 2. Okay, so we would subtract the mean sub 1 and divide by sigma sub 2 squared. So let's just kind of do that. Let's say, so the mean is 6, and so therefore 5 is less than 1 standard deviation below 6. Right? So this would get converted to maybe negative point, I'm just making up 3. 9 is more than 1 standard deviation above 6, so that would be 1.2, let's say. 3 is maybe 1.5 standard deviations below the mean. 1 is more than 2 standard deviations below the mean. And 15 is quite a few standard deviations above the mean. Right, so this is maybe 5. All right, let's just try this one. So 15 minus 6 divided by 2 equals 9, divided by 2 equals 4.5. So I was close on that. And similarly, we can do the same thing for 132, 0, 3, and 8. Let's just try it, actually. And here we'll use sigma sub 2 squared and mu sub 2, the mean. So 29, 100 is 30, about 7 standard deviations above the mean. 32 is like a 0.1. 0 is about 3 standard deviations below the mean. Three is maybe 2.5, negative 2.5, and 8 is closer to negative 2.1, something like that. So we know how to do that. We can do this standardization. The problem is this doesn't quite work right. We know how to do it, right? We could go ahead and just, when we get a batch in during training, look at these numbers, calculate the mean, calculate the standard deviation, rescale, and then feed it on. Do this for every column, and then feed it in to the next layer. So what we would do is basically add in a new layer, a new batch norm layer, and it'll do what I just described, do this rescaling. The problem is maybe this layer actually, so we go ahead and do this scaling. And now this layer says, you know what, as far as my backpropagation, I want to increase all 5 of these values. Partial L with respect to this output of this layer is negative for all of these values, which means they should all be increased. So it'll go back and adjust the weights such that these numbers come back up higher. So when we run again, the problem is, even if we adjusted it to make it higher, the normalization would still make it so that it's mean and standard deviation. If we just reran that batch, that would have no effect on the overall mean. So let's say it just wants these numbers to come out to be bigger. We would go ahead and rescale it so to be lower again. So what we've done is reduce the power of this network. We've said this network can never have anything coming out with a mean other than 0. And so that seemed overly restrictive. Before we put in the batch normalization, a layer was able to change the mean of what was coming out of the previous layer by the fact that the gradient could change all the weights and so on, and that would then change the mean. So we want to still maintain the ability for this layer to change the mean and the standard deviation, but we want it to be able to do it explicitly. So what we're going to do in this new batch norm layer is we're going to add 2 new learnable parameters. And I am going to call them mu sub bn and sigma squared sub bn. In the original paper, they just use, I think it's beta and gamma, right? Every paper, it's very difficult for them to keep track of which hyperparameters are used for which other papers. And so each paper just picks a couple Greek symbols normally close to the beginning of the alphabet. I'm going to use mu and sigma squared here because they have a special meaning for us. So they're tending to be the desired mean and the desired standard deviation. And these are going to be parameters that, let's say, will initialize the mean to 0 and the sigma squared to 1, but over time the neural network is going to learn what these should be. And we're going to have a separate mean and standard deviation for each one of the outputs of these nodes, that is for each column here. So what are we going to do for each batch? And this is during training. So for each batch, we're going to calculate the mean and the standard deviation. Okay, call that mu sub b for batch and sigma squared sub b also for the batch. Normalize to 0 and 1. So that is take the incoming value, so a, let's say k minus 1, whatever our previous layer is, and subtract the mean and divide by sigma squared sub b. So we're now normalized to the 0, 1 range. Now what we want to do is take it out of the 0, 1 range and take it to this range. So we want a mean of mu sub bn and a mean of sigma squared sub bn. How do we get that? Well, what we're going to do is go ahead and multiply by sigma squared of b. So that'll now scale it from being 0 to 1 to 0 to sigma squared b, and then add in mu sub b. Assuming these weren't changed from the one, so assuming we had these as fixed values, that'll mean as every batch comes in, it's going to get rescaled so that its mean and standard deviation are these values. And later layers can force the desired mean and standard deviation to what they want. But they do that directly by just changing the mean and the standard deviation, right? So if a later layer wants all the values to be higher, it can just, we would have a gradient here from the loss to the batch norm mean that would indicate whether it should be raised or lowered. So that would indicate whether we should be, you know, if we look at a curve here, let's say, if that's the curve of inputs, then, and this is the mean, then there may be a push to make the mean either higher or lower. Similarly, the standard deviation, spreading it out, can be directly affected. So there'd be a gradient that would affect this too. What we've got here is basically a reparameterization of our problem. So we did have our problem specified where our incoming values, we specified our incoming values as actual raw values, right, our A's. And now we're reparameterizing and saying that we are modifying these to be with respect to a particular mean and standard deviation, so normalized with respect to these. But there's still the same amount of power because the backpropagation can still modify the mean and standard deviation. We can add in then any batch normalization layer between any two other layers. So between layer k and k plus 1, we can add a batch normalization layer. This would now become k plus 2. We have now this batch normalization layer. There are no hyperparameters, but there are new parameters. So in this case, if this was size 3, the new batch norm layer is also going to be size 3. And we are going to be learning mu sub bn and sigma squared sum bn, and they're going to each be 1 by 3. Right? Because we are learning separately the mean and standard deviation for the first column, the second column, and the third column. That is for these nodes. So that's for training. What do we do about inference? Right? Because remember, at training time, how the batch norm is being used is we go ahead and calculate the mean of the batch and the standard deviation of the batch. Well, first off, when we're doing inference, maybe we're just inferring one thing. For inference, if we have a single item, then this batch is really small and doesn't make a lot of sense. Do we want to be using the mean and standard deviation of the batch that we're using for inference? No. So we don't calculate mu sub b or sigma squared of b. Instead, we use an exponential moving average of the training values. So we go ahead, and as we are calculating sigma mu sub b and sigma squared sub b, we store that in this batch norm layer during training. And then we continue maintaining this running average. Okay. So whether we use an exponential moving average or a running average, some sort of average, just to keeping track of what these values are, probably an exponential moving average. And then we go ahead and save this. So we make sure to save this in this batch norm layer so that it can be used at inference time. So we'll just go to add in here. Maintain an exponential moving average. The calculations for the gradient are a little more complicated, right? Basically, the derivative of this is a little more complicated. Part of what is happening, every other derivative we looked at, each instance in a batch was independent of one another as to what the gradient is. Here, the gradient is going to actually depend on the other values in the batch. So that's just a little new. But the nice thing is your framework is normally going to deal with this. So PyTorch, TensorFlow, and so on. So that's batch norm. Now the question is, why does this work? Why does this work as a regularization technique? And the answer is, like a lot of things in neural networks, we're not quite sure why. The current best hypothesis, and one thing to keep in mind is batch norm is relatively recent, right? This is within the last 6 years, let's say, like a lot of things in neural networks. So here's the theory of why batch norm works. So we have seen before some sort of a graph of loss with respect to theta. And so we might have, something like this. Okay? It might be very jagged. And so it can be easy to get stuck, for instance, in local minima. Our gradients will be changing, from positive to negative as we're going. And what batch norm seems to do is maintain the same minima. So we still have a minimum here, but it becomes smoother. So I'm going to draw it up above instead of right on top of it. All right. But we should put this down so that the minimum loss is the same as the minimum loss here. But what happens is it's just less jagged. It is smoother. And a smoother function, a smoother curve, is easier to use gradient descent on than a more jagged curve. So we can use higher learning rates, for example. That is the basic, best understanding right now of why it is batch norm works so well as a regularization technique.